So we'll just continue recording, I guess. Before I start, I just want to say thank you for everyone who's participated in the course. I'm pretty happy with how it went. And I got some good feedback. People seem to have enjoyed it, and people's minds were blown, or people were variously aggravated.
You did your job.
I did my job, I think.
Your job.
Hopefully, and now basically what I'm going to do is recap what we did. So we're going to go through very quickly for each case the various things that we saw, and along the way, sort of sprinkle in some interpretations of quantum mechanics. Now, each of these are going to be extremely brief. I think basically one slide for each. But I just want to be titillating. So you will then go look up each of these interpretations, so the ones that appeal to you based on my very brief sketching, and then you'll understand all the secrets of the universe, and we'll be done. So I have some pictures here. These are one for each of the interpretations that I'm going to talk to you about. I think it's 5, yeah, 5, but there's something like 50 interpretations. Okay, so these are just what I consider to be some of the most prominent ones. And so first, an outline. And I want to use the brief time that I have to branch about a little bit of stuff. Again, look back at what we covered and then intersperse interpretations. So, why did you want to be a physicist? Well, for me, it was the idea that we could get a deeper notion of what reality is by studying what we find in it, what it lets us do. And just in general, the theory takes the form it does because nature has certain characteristics. And, you know, this is my rant, by the way, I'm already ranting. Some people are happy to study the models alone. But I think that many of us were interested in the models in the first place because they had promised to tell us something about nature and reality. I mean, almost everyone that I know who went into physics, this was at least what they were originally thinking, and maybe they stopped talking about it as much.
We beat it out of it. We beat it out of it.
It get beaten out of you eventually. And some people would also say, like, okay, well, I'm studying the model alone, but reality is the model, maybe. Okay, maybe. There's this famous quote, statistician, all models are wrong. I think most people do have this instinct that the models are sort of, at best, approximate. So we still need to try to understand this original motivation. What is reality? And assuming the model is reality is confusing with that territory. It's another way of saying all models are wrong. So what is real? And we're in a different situation than we used to be because back in the day, the successes of classical physics seems to imply that reality is made of some stuff that is intrinsically detached from our observations, from us. You know, it's out there. It's detached from what philosophers sometimes call secondary qualities, like experience and stuff like this. And those things the reality might be made of that just sort of exists intrinsically, particles, fields, forces, etc. And this is, of course, a reasonably good idea, and it worked really, really well. Making this judgment was a large part of what allowed us to unlock all the explosion of scientific progress in the last 500 years. And indeed, it was only after incredible technological advances that any possible reason to doubt it appeared. Well, I should add some caveats to this because there were actually some Western philosophers who doubted it prior to quantum mechanics. And a lot of Eastern philosophies didn't subscribe to it in the first place, but we won't get into that. We're talking about the West here. Okay, measurement problem. Quantum theory strains that picture of there being things that are completely, utterly detached from us. And the reason, essentially, is the basic object, quantum state, seems to rope in an observer. There's two fundamental kinds of state change. There's evolution without measurement, and there's evolution upon measurement. And although the form is different, the evolution without measurement is familiar from classical physics, because that's typically what you do. You just say, okay, here's the system, here's my Hamiltonian, here's my equations, etc. It evolves. But evolution with measurement is different and challenges the idea that we can really be detached, as in fact measurement is our only empirical book on reality itself. So in a sense, we're sort of trivially not attached. How do we make sense of all of this? And that's basically my fast gloss of what people call And the measurement problem is the central guiding question of quantum foundations. I think that's pretty fair to say. And I think it's an important question because, in fact, the very nature of reality is at stake here. Kind of question we would ask is what kind of characteristics of nature can make it so that this theory is right? And if we are roped in, as I said we are, then something about that classical picture needs to be revised. And you can take different strategy or approaches to trying to resolve things. You could try to salvage as much of your pre-quantum intuitions as possible. Or you might say, well, maybe the reason this is different is because reality is profoundly different than we were imagining before. So that's sort of a couple of strategies if you want to focus on quantum foundations. But maybe all this philosophizing is unhelpful. And here's a couple of people who like to say things like that. And also there's David Merman, who came up with the term shove and calculate, although, by the way, he was making fun of people who say that. He doesn't believe that himself, but it's often misattributed to Feynman. Who are we to suppose anything about nature, right? I mean, that's a little silly because we have science. What does that do? Well, that reveals approximate truths about reality and replaces any need to philosophize. If quantum theory or any physical theory seems weird, you just need to adjust your expectations. Then, and anyway, prior to a theory of everything, why bother even trying to interpret it? So, these are the kinds of things that I heard when I realized that people weren't interested in reality anymore. Early on, I thought every physicist shared my motivation, but eventually I realized I was doing it. Felt like there was a bait and switch. Physics is really about what I thought. I told you I was going to rant. But just because you're in the minority doesn't mean you're wrong. And I know many of you actually do agree this is important stuff. And for the rest of you, consider that thinking you don't have a philosophy is very much like thinking you don't have an accent. And I'm from the Midwest, and these 12 states, and I know I have an accent, so consider what your accent is. Okay, random mostly Iowa. Living out Iowa, yeah. Well, I'm from Indiana. Okay, random mostly over. This course has been for those who don't want to shove and calculate, or at least I have thrust that upon you and forced you not to shove and calculate. And what did we do? We toured several of the technical landmarks of foundations research. The purpose was to get everyone thinking, organize those thoughts, in some cases question preconceived notions. And now finally, we get to say even at least a little bit about what sort of is most provocative about the entire field of interpretations. And armed with these concepts, we're better situated to have informed opinions, perhaps, about proposed ways to interpret quantum theory. So, we will review what's covered and weave in some of these interpretations along the way. Okay, welcome to something that is called the block universe by philosophers. There it is, this is the universe right here. And it's a block. This is the way the story goes. All of space-time is an unchanging four-dimensional block. Past and future are written, time and now are illusions. Basically, it's a God's eye perspective on the universe. And I would wager that most physicists actually have something like this in mind about what reality is. Maybe not quite, but something sort of like it. Certainly Einstein did, along with the insistence in particular that physics is local. So Basie showed us, well, introduced us to these three guys, Einstein, Podolsky, and Rosen. And in particular, Einstein was saying there shouldn't be an influence faster than light. This is Einstein's argument, not actually EPR's argument, but Einstein's was, I think, a little bit clearer of an argument. He basically just said, well, if quantum states are real, then the choice of a measurement at A, which is the things that you separated, affects the real state at B, which violates locality. And he developed relativity that was pretty precious to him. So certainly something has to be wrong with violating locality. He concluded quantum mechanics is correct, but not complete, because there should be some sort of underlying story in terms of other variables that interact locally that make it so that this statistical model makes the right predictions. Unfortunately for him, although he never saw it, this guy, John Bell, showed that this underlying description is impossible. The consequence is that you have to reject either locality or reality, by which I essentially mean this block picture. So one of the two can't work, as they showed us. And I'll just mention for now that often the word quantum non-locality, that phrase is used to describe the impossibility to have both as a broad umbrella term for really you have to reject one of these two. More generally, even than what Bell did, is the Cauchy spectra stuff, contextuality. You can say that in some circumstances, quantum theory is simply inconsistent with simultaneously ascribing elements of reality in different contexts, across different contexts. And I say it's a special case because non-locality is a special case in which measurement contexts contain measurements that are distributed over space-like separated regions. So, okay, quantum mechanics is contextual if you want to try to view it in the block type of picture. So, what do? Since quantum mechanics is not incomplete, should we then just conclude that objects are real, even if spooky to Einstein and to others? Well, that I can sum up that attitude with meme. All talks are meme. You hear quantum mechanics wearing a shirt that says, "You may not like it. This is what performance looks like."
So, since quantum theory is not incomplete, so since quantum theory is complete,
Yes, sorry.
wait, and it is complete?
Well, I mean, it's not incomplete in the way Einstein was talking about. That's what I mean. Yeah. So since we don't have these underlying hidden variables,
Local hidden variables.
yeah, local. Since we don't have these underlying local hidden variables, then we should just say, okay, this quantum state's a real thing. You may not like it, but this is what peak performance looks like. Well, indeed, you can fit all of this in a block. You just got to make it bigger, more larger, unwieldy quantum states of the elements of reality, and now your block is maddeningly complex. Personally, my take is it's better to conclude that measurements are generative rather than revealing, but there's no common taste. So let's just sketch, roughly speaking, how this goes. Interpretations typically fall into one of two categories. First one is called psiontic interpretations, which take the wave function to be a real physical thing. And so naturally we call believers Scientologists. Epistemic interpretations regard the state to be a measure of our knowledge, information, or belief, some sort of thinky-winky kind of thing. Okay, our first interpretation is actually a modification of quantum theory. It's called the DeBrota or Bohmian mechanics. Typically people usually just call it Bohmian mechanics. And it basically says, okay, reality has to be non-local, fine, let's do it. Let's construct a model. And I'm not going to show you any math in any of this, just sketching how the way things work. But basically, we have the whole wave functions, and we have a wave function of the whole universe. And that's interpreted as a pilot wave that guides conditional real things, namely particles, in their flow. And so the flow now is non-Newtonian, but they still move around in like a classical pre-existing deterministic way. It's not classical in like Hamilton equations, but there's always a position of a particle that moves in a particularly exactly determined way. And this is a very holistic kind of picture because this pilot wave, the whole universe, this pilot wave, participates in determining the behavior of every particle. By the way, this picture is the trajectories that you could get for the double slit experiment. So each of these is like a particular particle trajectory you could have according to Bohmian mechanics. Physical position properties like position and momentum are deterministic. Outcomes pre-exist the revealing measurement. So by the way it addresses the measurement problem is measurements what you've always thought. It just reveals truth. Okay. It has some issues once you try to make this go beyond very, very simple situations. So like, for instance, making it work with relativity is unclear whether that works, but maybe it does. Maybe possible. There's your Bohmian mechanics.
John, I never studied it myself, but how does Bohmian mechanics give me random outcomes? There are hidden variables.
Yeah, there are hidden variables, and they're non-local.
They're hidden variables.
Yeah, so it's a variable. Yeah, so then my particle is a hidden variable. I don't see the particle directly except when I make a measurement.
But there's something that tells part of what to do, but I don't have access to that something.
Yeah, right. Another one is also modification, so I'm getting both, yeah.
Doesn't that imply that, like, there is an interpretation where quantum mechanics is incomplete?
No,
This is the modification of
complete, it's there, it's just, I mean, that's, Einstein said there are local variables. I mean, they're hidden variables.
And this is the non-local hidden variable. See what I mean? So it's not local, so this is a non-local completion, which would have still pissed off Einstein.
More.
Would have pissed him off more, actually.
I think it's, but it is called an interpretation.
I'm being a little, I mean, some people call it an interpretation, but indeed it's a modification of quantum theory. So, in that sense, at some level of description, it probably makes good predictions. People do say, you know, potentially you can test whether quantum mechanics.
See, that's awesome.
Yeah, but I just think that's
Something falsified.
And then falsifiable theories.
Another one that is potentially falsifiable is spontaneous collapse models. That's not one. It's another strategy. So this one directly tackles the problem by modifying quantum mechanics so that collapse is part of the dynamics. So basically, you say unitarity itself is approximate. Schrödinger equation is supplemented with additional nonlinear and stochastic terms, which play the role of localizing wave functions. And any interaction can trigger a collapse, which typically would be extremely fast, otherwise we would sort of see these happening. And the probability of collapse approaches certainty as the number of interactions increases. There are many distinct variants of this, depending on how you want to model your noise, how you want to model your stochasticity, there's different colored noises, stuff like that. Two open problems, I think, for all of them is how to combine these again with relativistic locality type considerations. And then, of course, since we don't have unitarity, then energy is not even conserved for isolated particles. But for those of you who have this feeling that all of this stuff we talk about in foundations about applying wave functions to like Victor and all this really big stuff, you might say, well, why are we all pretending like quantum mechanics doesn't break down? And so people are attracted to this. Okay, well, maybe, you know, it's just we haven't seen it collapsing and stuff like that. Like, really, that's the physical thing. It does collapse stochastically, and this Hilbert space stuff is approximation. So some people may be attracted to that kind of a interpretation, although again, this is a modification. Okay, so those were both ontic, psi-ontic interpretations, so to speak. But again, how is epistemic interpretations actually an option? Because didn't Einstein, Dvosky, Rosen, and Spacey basically tell us that a state is not simply equivalent to a probability distribution over a true state of affairs or hidden variable optic state, whatever you want to call it. So how can I even have epistemic interpretation? I want to just say that what Leroy did then, following up on that, was gave us a powerful argument for why quantum theory perhaps is nonetheless at least partly of epistemic character. And he did so through Rob Spector's toy model. So the toy model was an explicitly local and real toy theory, to which we simply impose an epistemic restriction called the knowledge balance principle, which means like I can know a certain amount, but I can't know more than that. And if I just say that for whatever reason that's always the case, we saw that that produces analogies of most so-called quantum phenomena. So for instance, non-commutativity, interference, cloning, entanglement monogamy, entanglement monogamy, teleportation, dense coding. There's a whole lot more actually. Basically, you know, if it can get you all of those things, and all you needed to do was impose some sort of epistemic kind of, well, in this case, restriction, but epistemic lesson, then that really makes you think that a lot more of this than what you get just from the formalism is about our information or our knowledge or our beliefs. And, you know, it calls to mind, of course, the famous James quote. So I say we want to isolate what is truly special and different, not wade around in a theory, which is what he said, in part realities of nature, in part incomplete human information about nature. Okay, so speaking of epistemics, let's actually even have our first so-called epistemic interpretation, the, in quotes, Copenhagen interpretation. I put it in quotes because it's not a single interpretation. It actually, I mean, to say that, perhaps most people are aware that it's not just one particular dogma, but the term refers to a collection of ideas and perspectives associated with some of the founders, Feinberg, Bohr, Howley, But most significantly, Niels Bohr, and here's a picture of the Niels Bohr Institute, Copenhagen. It wasn't called that while he was still alive, by the way. Kind of cool if you like works as Niels Bohr at the Niels Bohr Institute. But they only named it that 3 years after he died, so. Basically though, and I'm more or less siding with what Bohr says, and of course there are differences between different founders, but broadly speaking, state is of epistemic character, so something about our information. And measurement, which Bohr called irreversible amplification, then leads to information update. So measurement is just what you're learning, okay. And you update your knowledge, and you can have objective knowledge. That's sort of an important point. And the irreversible amplification, like you're always talking about, like spots on photographic plates and stuff like this, that then anyone can view, and it's sort of just out there in the world after measurements are made. Another important aspect of the Copenhagen interpretation is that so-called knowledge that you get is always going to be context dependent. And if you ever try to read some Bohr prose, which I do recommend you look at it, but I also warn in advance that it's very like elliptical. Because some sentences are like half-page long. And by the time you finish the sentence, you're like, oh, that's nothing. Wait, what did that say? Yeah, so it can be hard, but that doesn't mean that he was just crazy. And there's a lot of people who have put a lot of time and effort into decoding what he wrote, and he had some pretty interesting things to say. He's always talking about how the experimental arrangement, so to speak, cannot be taken out of the picture. So if you want to talk about these quantum things, the effects of photons and electrons and all the things that you're doing, then an essential part of that comes from the larger classical physics world of ordinary language, classical physics, because only with respect to that does it mean anything to us, essentially. And so he's always talking about two different distinct realms. There's sort of a classical realm and a quantum realm. And the quantum realm actually depends on the classical realm, as opposed to a sort of other kind of intuition where you would say, well, of course, the quantum realm produces the classical realm. I think he would also agree with that statement, but it's sort of hard to talk about. So, important thing to know about the Copenhagen interpretation is it's always bringing in, well, essentially like reference frame kind of stuff, sort of classical light stuff. Depending on who you are, you might talk about that in terms of specifically classical physics or not, but in any case, there are different realms at stake here. I think the biggest takeaway from this is that this type of strategy is the first one we've talked about so far that says that quantum mechanics profoundly changes how we should understand the relationship between system and observer. First two were just like, no, observers, let's do whatever we can to get rid of them. And this one's like Copenhagen, the so-called textbook interpretation says, okay, well, observers are there, and we're going to work with that. Okay, then next, Robbie basically went deeper into the idea of foil theories and reconstructions. So the toy model that I told you in seconds was our first foil theory. Another one that we got from Cole was the Pescarolic box. What is that? That provides a non-signaling foil, which is more non-local in quantum mechanics. It's still non-signaling, but it's more non-local. And from the perspective of foils like this, you realize you can be more non-signaling in quantum mechanics, and you immediately ask, well, this is sort of the foundational question: why do we have precisely this much violation of Bell inequalities? It's an important question to answer. Robbie told us about the generalized probabilistic theory framework, and that allowed for constructing any of the landscape of epistemic foils based on whatever context state space you wish to use. And again, here you basically can then ask, well, what makes the place in this landscape that is quantum theory actually special among these? And thinking about that has led to various kinds of reconstructions within this framework. I think we heard about one or two from Howard Barnum when he was here last year. Robbie also told us about the modal quantum mechanics foil, which cut things up differently than the Speck's toy model. It actually does reproduce Bell inequality like violation. Didn't have other things. I don't want to talk about that much because I haven't read about it much myself. Okay, Victor's former roommates. I had maybe too much fun coming up with titles on these slides.
We appreciate it.
I I say former roommates because, you know, I don't remember, I think it was Scott Erickson said, you know, I kind of borrowed your friend, or something like that.
But you do your roommates.
You do your, I mean, former roommates, obviously they're not living together anymore. So Andrew and Mosen managed to enrage all of Seaquick with their coverage of the extension of Bigger-Spence paradox. And I applaud them for this, because that was my goal. Basically, the original Bigger-Spence paradox was about Bigger and the so-called friend that was in the box with the two-level system or something like that. Friend is going to make a measurement, get an outcome. Bigger's on the outside and it's closed to him, so he treats the whole thing as unitary evolution. For Bigner, there's no measurement outcome because it's just unitary evolution, but for the friend, there is a measurement outcome. And so you could ask who's right, and in fact, Bigner would even undo the measurement outcome of the friend by further unitary evolution. They could talk, be like, well, what'd you get? Well, do you remember that you got anything? Or like, what's real? Like, what's going on here? That was something that upset some people and motivated different approaches and different interpretations back in the day. Bigner himself thought perhaps that the answer is that consciousness itself leads to the collapse. I don't think anyone serious actually believes that anymore. And certainly the other COVID negatives didn't. So I don't really see why Bigner is called a COVID negative interpretation person, but anyway, let's not worry about that. But it really came before, like 10 years ago, roughly now, because people started wrapping up the Bigner's paradox in like CHSH inequality violations, contextuality demonstrations. Now it's personal because now we have like a literal theorem that says you believe these things. Okay, well, one of them has to be wrong because you tied yourself into a knot. And you might recall the Q, S, and C assumptions, quantumness, single outcome, consistency, roughly speaking, and how you answer which one you have to reject depends crucially on what you think one is. And so at the end of that paper, Krasher and Renner made a grid showing a bunch of different interpretations, one we're going to talk about here, and basically told you how each one responded to each of these assumptions. And you may remember many worlds had 2 question marks and an X. Like, it's a really sad state of affairs. Well, let's just use this as an opportunity to segue into many worlds interpretation. My arch nemesis, but I'm not going to let my feelings get in the way too much. I'll be waiting in the end, we already have. So, what is the many worlds interpretation? It basically solves the Benjamin problem by saying there isn't one, because wave functions simply don't collapse, okay? All you need is unitary dynamics. The universe is a deterministically evolving state vector. And people in many worlds church like to say, well, look how simple this is. I actually got rid of one of the postulates. Like, so I'm taking the theory even more seriously, and if I don't need to have a measurement postulate, then I'm better for it. And I do agree with that basic kind of an argument. You really can't get rid of it, then go for it. But then what do we need when it happens? And typically the story goes that at moments of measurement, the universe splits in air quotes that are very necessary here, because exactly what you mean by splits is very contentious. But okay, let's say it splits into worlds where an observer records different outcomes. And so the fact that the world or these universes all happen and all the different records occur, then in that sense, it does violate S. That was the 1S and X previous slide, yeah.
I have a question. What do people in this church say to the charge that like, we don't think quantum mechanics is complete, doesn't include gravity, or doesn't gel with gravity? How could it be just an evolving vector in element space?
Good question. I think I heard Sean Carroll try to answer that before. But I agree with you that it, like, you know, according to a future theory of everything or whatever, something like that, maybe it's not a state in an open space, but my guess is that they would say that whatever different theory you do have, it's still going to be a state of some kind, and so that's going to just be the real thing. That's my guess. Okay, so S is violated. That one is not so troubling. But I should also note that just like spontaneous collapse, this is really a family of interpretations as well. Basically, everyone who espouses many worlds has a slightly different view. They disagree with each other. They just sort of all agree that essentially the wave function doesn't collapse. That's sort of the overall unifying theme. So some of them don't even talk about the universe splitting at all. They just say, oh yeah, people talk about these splits, but that's not really what's happening yet.
Yeah. So an anecdote. So Sean Carroll has a program where he's trying to get gravity out of out of quantum mechanics.
Okay, right.
So they say quantum mechanics is everything, and we have to get gravity out of it somehow.
Sorry,
And-
so you would
Lorentz
modify it,
invariance.
Yeah, and Lorentz invariance and everything. And secondly, when they say split, they say all these branches are so like Sean Carroll at least said this, that all these branches exist. You just find out in which branch you are. It's not that they are spontaneously created. They were just there, and you didn't know which branch you were in.
Yeah, so there's the Carroll interpretation, but Wallace has a different one. I think Maudlin has a different one. I think there's all these different philosophers of science who subscribe to variance of this, and they all think all of each other are wrong. I think it really comes down to whether the branching supposedly objectively happens. Because if the branching is like really happening, really, and that's sort of part of the ontology of the world, then how you answer whether they reject or accept Q and C depends on how you answer those things. I don't really understand the details here, but that's why Rauschning and Renner with question marks. It's because there wasn't one coherent dogma. And then I should also mention that decoherence itself is sometimes invoked to explain why world splitting is effectively irreversible. And also, I should point out there is a similarity with Bohmian mechanics, because in Bohmian mechanics you also have a universal wave function. Except instead of saying, okay, now we're also adding true, real particles to the picture, many worlds people say, oh, no, that's extravagance, we don't need that. Instead, let's add extra universes, so that's less extravagant. So, that's it for many worlds, but is it? Well, no, because rant 2 is here, electric boogaloo. I just want to like push back on something that I often hear from many worlds people. I know this, I'm not even arguing against people who even said this to me, but many worlds interpretation is motivated to save quote unquote reality, which again is the black universe. And for instance, John Prescott in some notes online talks about things and just says, well, I believe in reality. Like he says that when he talks about why he says he believes in many worlds, as if believing in reality implies Scientology. I think this misses the point. Just because someone doesn't think a state is real doesn't mean they think nothing is, right? And I think most of all, for me at least, for many worlds interpretation, state is real, despite everyone knows. It's sort of like a ghostly thing. Like no one watches a state. It's not something you can hold in your hand. You always use it as a tool that is sort of indirectly assigned. So it's a ghostly thing. Whereas measurement, again, the only part of this theory that connects us to experiment and to reality, that's the illusion. So I don't know. That's the thing that annoys me about many worlds. And also, Jalen just argued today that without extrinsic factors, like say someone there to write down state, in my opinion, a state evolving alone cannot provide its own interpretation. Okay, then Ivy basically drew our attention to the asymmetric way in which quantum theory treats time and space. So remember in spatial, space is treated with tensor products. Time is just the same built-in space that evolves. It's an interesting situation because that isn't what we had before in classical physics. But a nice thing is that nevertheless, one can collect everything into a single process matrix formalism, which does use the usual form of tensor products, and then you can study those process matrices. And Chasov Bruckner and company worked in this operational setting and were able to see that theory does not seem to prohibit particular kinds of exotic causal behavior. And that which is not forbidden is mandatory, potentially. And the situation is reminiscent but distinct from entanglement, which you can couch in terms of violations of Bell-like inequalities. In entanglement was mandatory, and it was It's not exactly parallel in the process matrix setting. I actually don't know what to make of this stuff quite yet. I'm planning to read more about it, but I thought it was very cool. Which did too.
So this is not quantum field theory, it's just regular quantum.
Yeah, I think they use the word process matrix too. This is a different, I think it's a different thing. And finally, let's push on the this epistemic side of things again. Because, you know, fine, maybe things are epistemic, but even if states and so forth are epistemic, then it seems like we can get them right. And if I can get it right, then okay, you're just splitting hairs when you talk about, oh, this is my information, because like really it's just like, okay, I don't know it, but it's there, right? So then it might as well be a real thing. Similarly, I mean, same thing I was just saying, we can have unknown states. And this seems to be implying that when I say epistemics is about like knowledge, information, or beliefs, well, we're really talking about what philosophers call knowledge. Okay, it's like truth or information about truth, whereas belief is really not so truthy. So Chaitanya and Shravan told us about the Many theorem and theorems and various things in that sphere. And the nice thing about that was that it gives an operational meaning to the idea of an unknown probability or unknown quantum state. The key was the idea of an exchangeable joint prior. So you have an exchangeable joint prior if you believe that the order of the data that you can obtain is irrelevant, and that this would be true regardless of how much data you can collect. And so then the Definite representation theorem says, well, if you hold an exchangeable joint prior, then you may reason as if you have many copies of the same system with a prior density. It basically operationally tells you the sense in which if you are a subjective Bayesian, who thinks the probabilities are all about belief, it tells you what does it mean to think that I'm repeating the same experiment. And so another lesson from that is that quantum states need not be, and more provocatively, perhaps cannot be, properties of a system, just as a bias is not a property of a coin. Bias is about you, it's not about a coin. Coins are heads or tails. Okay, look at that. It's my favorite interpretation, and I'm only going to give one slide to it, so listen closely. People call this the radical epistemic, or even sometimes doxastic interpretation, where doxastic is one of these philosopher terms which means concerning belief, whereas epistemic technically means concerning knowledge. So more properly, cubism is doxastic. And it takes the agent's actions and experiences with the world as essential concerns of the theory. I think I've talked to a bunch of you about this, and you probably heard from me before. So maybe it's not worth belaboring too much, but there are some similarities with Copenhagen style interpretations. Although in pretty much every point-by-point comparison, cubism goes farther, I would say, more radical. It's also characterized by a strict adherence to this Bayesian interpretation, which is why Definite theorem is so important to me. And what does that do? Well, it renders quantum mechanics itself as a normative addition to a decision theory. And that means that what we have with theory is not a directly physical theory in the same way that most other interpretations take the theory as another typical kind of thing physics has produced in the past. So we're saying that it's different, and that when you want to understand reality, you have to understand it in terms of the shape of this decision theory. States, measurements, even outcomes are personal, subjective aspect of it. And also measurement apparatus is a conceptual extension of the agent. However, there is some objectivity because the overall structure has to be the same for anyone who uses it. So that's the thing, that's the glue that holds us all in the same universe, because we are all subject to the same decision theory. Measurement is fundamental as opposed to dynamics being fundamental for many worlds. So it's pretty much the inverse of many worlds. See my recent paper about that. And then just in general, it rejects the black universe picture and tries to find something to replace it. Now, don't come at me with what's your ontology, because that's part of the research program, okay? Rather than postulate one, like most interpretations do, we say we don't really know, we know it's not like that, and we're looking for one. Okay. And our final interpretation is called relational quantum mechanics, and it comes after cubism here because in some ways it's the one that's closest to cubism, but it's different and you may not have heard about it. So it's due to a guy named Carlo Rovelli up here, atomic physicist. I think most of the time he works on quantum gravity actually, but anyway, he came up with this interpretation in the 90s. And it has some similarities and differences to cubism. It's somewhere, I guess, actually between epistemic and ontechnical. And in general, it's an attempt to make quantum mechanics like light and relativity. States are epistemic, but they are also sort of, I mean, they could be right and wrong. I mean, there's a right state, and but it's always relative to another system. So everything that you talk about is always from some particular situated perspective. And the way you interpret what a state is that you just say, well, it's just a description of the objective correlations of some degrees of freedom in the observer with things being observed. So it's always this binary.
How is this different from correlations without correlata, which was Merman's
right.
thing?
I don't remember the details of correlations without correlata. Although
It's basically that.
And I mean, I think that fact alone, I think is the same.
But there
may be differences. Yeah, I don't know. Yeah, I should go back and see exactly what Merman is saying. I mean, this was before, I think, correlations without correlata, actually. So presumably Merman had something slightly different in mind, although I don't remember what. This was 96, I think Merman.
Yeah, that was later.
2000.
I don't understand the last point here. I thought intrinsic properties means these are properties independent of other systems, right? But it seems like
maybe intrinsic is the wrong word. I don't know. I wrote that, but properties are supposed to be like true, but relative always. So you all like what you can say is always from like this. From this observer, this thing is true. From this observer, this thing is true. And there's no global picture.
so real, but like Nietzschean.
Oh.
Like Nietzschean.
It's not like potentially. Yeah.
Is it kind of like the distance from me to him is something, and then from him to him is different? Like, is it like?
I mean,
real
those
that
things are true, but the key really is that there's no picture from nowhere that tells you all the distances that are sort of true. The distance from you and you would be like true with respect to you, and maybe it's not even necessarily compatible in different kinds of respect. And in that basic way, that's a pretty close similarity with cubism, but there are some pretty big differences. One of the biggest differences is that Rovelli says that any system can be an observer. So he really wants to abstract away from
Humans.
Yeah, humans, or the idea that agency or observership has anything to do with this. We just want to say there's a physical system and another physical system, and there's a fact of the matter about what the quantum state is from this situation, or from this situation, or from the third situation, and so forth. Measurements are also just interaction. So in between interactions, nothing can be said at all. So there's a lot of, we can't talk about that going on. It's kind of an interpretation. A grain of sand can be an observer. Whereas I wouldn't usually think a grain of sand can be an observer, because I don't think a grain of, as a cubist, I don't think a grain of sand can think about what quantum state it should use in a particular situation, right? So that's a big difference. I already said this, different observers can give different accounts of the same sequence. So let's compare it. Well, like many worlds interpretation, it indexes branches of superposition, but unlike many worlds, this is only one world, and those indexes are talking about different relational quantities that could be real depending on which position you're actually looking from. Like Copenhagen, it focuses on the interaction between observer and system. But unlike these interpretation, there's no special role for the macro world. And like cubism, it emphasizes the essential role of perspective, similarly rejects the block universe. However, probabilities are objective for Rovelli, in my opinion, to his own detriment. And any system can be an observer. I think those are the biggest differences. There's other differences too, just because, you know, it's talking about states being sort of real. I don't think that makes any sense ever. And of course, I can't help but just say that if this is all sounding really good to you in like attained cubism, and I don't have to go so far to be crazy like those cubists, I will just point you to this paper, which basically finds, well, it dismantles our cubism, in my opinion. And also it's unfortunate because even though it came out in 1996, it's changed like every 3 or 4 years. He like adds something or changes something. So it's actually not clear to me exactly what argument is in its finest details. Anyway, a quintet of quandaries. No go through those. Okay, we are vastly over. I went way longer than I planned to as well. There are many more interpretations. I invite you to read about them and then consider how they fit into the concerns we raised during this course. Always be auditing your own philosophy. Is it consistent? Is it useful? These are my motivational speech. And then be open to the possibility that things aren't the way they seemed. Don't forget about reality. Thank you for your attention. I went to 5:30, and I explicitly said I didn't want to go to 5:30.
You didn't go beyond 5:30, which is what you said. Please speaking, you are
Did you turn off the recording?
oh,